This podcast is brought to you by the Albany Public Library main branch and the generosity of listeners like you. What is a podcast? God, Daddy, these people talk as much as you do. Razib Khan's Unsupervised Learning.
Hey everybody! So we got another episode of the Unsupervised Learning Podcast, and I'm here with a friend of mine, Dr. David Mittelman. We've written 3 genome biology comments together, so we've known each other for a while. And I wanted to get him on because he has an interesting journey of going from academic science and his various passions in genomics into the private sector. He has a new business right now, running, doing forensic genomics, and it has a very big human angle that I think a lot of the listeners will be interested in. So, David, could you introduce yourself?
Yes, my name is David Middleman, and as you noted, I've had a lifelong fascination with human genetics, much like you. I started out in the Human Genome Project. This was in the '90s at UT Southwestern in Dallas, and did a lot of the technical work to help automate and streamline sequencing that first genome. I trained at Baylor College of Medicine in Houston. All of my work is centered on some aspect of DNA testing or gene editing or DNA repair. And like you noted, has spent quite a bit of time at the universities, writing grants, running a public lab, and then eventually transitioned into private industry, where I've worked on a few different startups, most all of them centered around some aspect of genetics.
Yeah. So, can you talk about like what your start in science was first?
I guess my very first start, I was hired to work in a machine shop and build kind of components to automate and improve the robotics for the first human genome project. So I didn't have any formal training in biology, and I was building all sorts of gadgets and gizmos, um, Rube Goldberg machines to basically help make the sequencing process with Sanger sequencing less painful. Even included finding ways to streamline how you automate gel electrophoresis for hundreds of clones that you'll then have to put through shotgun sequencing. So a lot of stuff people don't have to worry about anymore. But anyways, cool to say that I was able to work on those projects. I later got more involved in data analysis and in trying to understand what all this information that we were generating meant, and kind of spurred an early interest in bioinformatics for me. But around the time that I was getting ready to make decisions about graduate programs, I really had a deeper fascination in just DNA in general. How does the whole process work? What does all the informational content in a genome mean? And that took me to Baylor College of Medicine, where I did a very traditional, heavily biochemistry and genetics focused graduate uh, degree.
Yeah. So, I know a little bit of your background. Obviously, we are friends, and I want to emphasize to the listener it's interesting from my perspective that I feel like a lot of your interest in science has a strong technological component. And so, people think of scientists a lot of times as a kind of, head in the clouds, very abstract. And I feel like, you've always kind of gotten your hands dirty and gotten super interested in kind of the process and the methodology. Like, would you say that that's correct?
Yeah, there's many people that like science and are in science for different reasons. And although I trained alongside scientists, I would say I'm more a tinkerer and an engineer. And so I'm very interested in understanding things about science, but I also want to deploy them. It's always been my dream to see the technology that grew up in the universities deployed to actually real people, whether that's to the clinic so people can use this technology to advance diagnostics, whether it's for some other reason. Um, you know, I just want to see technology leave the university one day. Not get trapped in that paper that like your collaborators and mom and dad read, and really make it out into the real world and do something useful.
Yeah. That's totally true. And you mentioned speaking of technology, you mentioned Sanger sequencing. Um, so this is 2021 as we're recording. And it's kind of incredible how far we have come in this technology in a bit over 20 years. Can you tell the listener, because I know a lot of listeners are geneticists, but a lot of them are not. And I know what you mean by Sanger sequencing and electrophoresis. Could you actually lay out for the listener of like what it was like pre-technology, pre-quote next generation sequencing, high throughput?
Yeah, sure. It's a good thing to talk about. So there's a lot of contrasts in the Sanger sequencing lab setup. There was a lot of lab work, a lot of hands-on lab work, and then a little bit of data coming out of the machine. Whereas nowadays, there's very small footprints of lab that are necessary, powered by these machines that look like iMacs that produce gobs of information. And so, whereas early on, a lot of the technology development was centered around trying to build automation and lab infrastructure. Now a lot of it's centered around bioinformatic analysis and management of what people call big data. And Sanger sequencing, it was an innovation in itself. That allowed, and when the automated sequencers came out in the late '80s, it allowed folks to use a very simple fluorescent based system to read out chunks of DNA. So you put a piece of DNA, and through the Sanger method, you could use fluorescent tags to indirectly read out what the sequence of a DNA sequence was. And the innovation that happened in the mid 2000s is that there were these several companies, of which Illumina was one, but not the first. Several companies that came around and said, what if there are ways to parallelize the process and read lots of pieces of DNA at once? And specifically Illumina, they developed this approach, sequencing by synthesis, where they really took something that's very similar to Sanger sequencing, this fluorescent detection of basically a DNA sequence, and they removed one piece of this process, and essentially made the addition of these fluorescent dyes reversible, and then created a kind of a two-dimensional space, a grid, which is called a flow cell, and enabled people to basically take lots of different pieces of DNA as opposed to like the one piece you're looking at with Sanger sequencing, lay them out on a kind of on a matrix on a two-dimensional space, and sequence all these little fragments at once. And so what's great about it is that it's cost effective. There's a fixed cost to run the sequencer. It's fast because you're getting lots of pieces of sequences at a time. And the downside is that you get gobs of data, and the segments, these little fragments or reads as they call them, don't come out in any specific order. You just get like a big text file, you might imagine, with just a lot of letters. So that's basically the two differences. You had kind of the original way of sequencing with Sanger, the Sanger method, which in itself had many iterations, but most recently was a fluorescent based method to read in aggregate one chunk of DNA, and that gave, and those were kind of that was how people did medical diagnostics then. Even now, people will verify very often things they see in the DNA in a clinical context using Sanger sequencing. And that gave way to this new method, which, like I said, is a small lab footprint. The equipment's become very streamlined and automated. It becomes very easy in the lab to generate the data. But then you get these gigantic files that have gobs of information in them. The other big thing, like zooming out past the technology, is that we spent over a decade in the public sector building out this this incredible system to read out what became known as a human reference sequence. So it's not any one person, but it's a representation of what a human genome looks like. And now with next generation sequencing, as they originally called it, I just call it Illumina sequencing. That's pretty much what people use now. You have the ability to read out lots of people's genomes all at the same time, and you can start to ask interesting questions that I know, for example, will interest you, like questions about population genetics, how we vary, how subgroups of folks vary from other subgroups, and it's just been fascinating. And all of that's happened, kind of within the same time frame that I went from starting to finishing graduate school. So just a very very quick pace, and you zoom to today where it's become just incredibly cost effective, and because it's cost effective now and also straightforward to sequence and read out people's genomes, you can do all sorts of interesting things. And so there's a lot of our verticals that have emerged that are powered by sequencing.
Yeah, I mean, to reiterate what David's saying, basically, Sanger sequencing in the 1990s, a lot of it was manual in terms of people literally reading things out, right? And I was in a lab at one point in the early teens where they were still doing some of that, and there were Word files that they used to save the data, the output data, and it was just very primitive seeming to anything we would do today. I mean, this is a technological revolution that has been driven by the fact that we do have automation available and that we do have computers. So you mentioned, David, that there's all these, you know, reads, these little strings coming out. How would a regular human ever reassemble that? It's just not feasible with 3 billion base pairs, a sequence that long, 2.84 gigabases or whatever, gigabytes. Uh, you're not going to be able to do that manually. I mean, you could, but you have to devote a whole nation's economy to doing it. And so this was not really even imaginable before the age of computing. And so the interesting thing here is genetics, human genetics, predates computing, right? It dates back to the beginning of genetics in the early 20th century, and they were trying to figure out inheritance patterns in families and, how diseases are inherited and maybe where in the genome it was based on a genetic map that they used some sort of marker associations. It was all very theoretical, high level, and there was really no feasibility of actually getting a whole map. I mean, in the beginning, they didn't even know the DNA was what the inheritance was. It was the substrate through it was transmitted. We knew so little. So you go through the molecular biology revolution, and people understand what the substrate is, and then in the 1990s. Computers start coming online that start to have some serious power. Automation becomes a big deal. There's all sorts of things that have come together to bring us in this technological moment where the first human genome is $3 billion, and it takes about what is it, like 13 years for the complete, quote unquote complete, not really complete, but whatever,
The
complete-ish,
completed draft.
yeah, completed draft. Um, and now in your own lab, you are sequencing people, like you are doing genome sequences, right? So that's how far we've come in less than 20 years. Something that was $3 billion to something that is feasible for your own company.
Yeah, I mean, even when I was at the university, I had a lab briefly at Virginia Tech. They had started this new bioinformatics center to explore topics in human genetics, and I got recruited as a young faculty member. And even then, when we were there, this was the I think early 2010s. It's about 10 years ago. It was still tens of thousands of dollars, still over $10,000 to get a good amount of sequence data from somebody. And you can juxtapose that to the last couple of years as it's become, it's gone from like the low thousands to even sub $1,000 under certain circumstances.
Yeah, yeah. So I mean, it's dropped kind of like on another tenfold drop, you would say.
Yeah, yeah, and I mean it'll plateau. I hear in the news that one day it's going to be $100. Can't wait. But for now, it's kind of hovered somewhere around $1,000, and these numbers are all estimates. It depends on throughput and obviously the application and everything else. But for a germline, genome from a buccal swab, if you run these in mass, you can get them under $1,000. Is what Illumina says.
Okay. Yeah. Well, so that's where we are with the technology and with the genetics. You left Virginia Tech a while ago, and you've been through some companies. Your current company that you're working for, Othram, is really, really leveraging next generation sequencing to a kind of a different space. And I think a lot of listeners will have watched CSI and these sorts of shows. They'll know something about it. So you're focused right now on forensics. Can you talk about where the forensic space, has been? I think a lot of people know the technology from television shows, but where really was it,
Yeah.
at least in terms of genetics, which people know about? Where do you want to take it? Like, what are you able to do now, etc.?
So yeah, I guess from television, you've seen on the CSI shows where they're running the electrophoretic gels to generate the STR profiles. That's really the gold standard in forensics. It's interesting because those profiles are run basically on the same machine that you do Sanger sequencing with. But instead of reading out sequences, they're measuring the sizes of these things called STRs, short tandem repeats. So they're measuring the sizes of these repetitions. How many times these little DNA sequences repeated over and over again? And they repeat in a very highly variable way from person to person. So the idea is if you grab a set of these STR markers, and they're all variable from person to person, if you grab enough of these markers, then in principle you can uniquely index someone. And if they leave DNA at a crime scene, you should in principle be able to identify whether or not they were at the crime scene or not by including or excluding the possibility by comparing these STR markers. And the program is called CODIS. This framework grew from the early 90s, even a little bit before they started using STR testing. And over the years, they've increased the number of markers. In 2017, I think they increased it to 20 markers. So there's 20 markers that that I think are used right now to index people, and you can use it to track repeat crime. It's a really effective approach, actually. For Zeeb commits a crime, in California, and then you're caught and they index you, and then you come to Texas and commit a crime. If they pull the markers from the crime scene, they can compare them against your profile that was generated in California and say, Razib was at both places. The challenge with CODIS is that there's only 20 markers, so the amount of information you can glean is very small, and it's really only useful in confirming that you were at a crime scene. Sometimes, in the best case, you can do what's called a familial search and identify perhaps a parent child or sibling relationship. That's pretty
Yeah.
much it. And so beyond that, you're really out of luck.
Well,
And
let
yeah,
me
go
let me
ahead.
let me take it a step back for the listener. You're saying 20 markers. Just to give a sense of perspective, there's 3 million base pairs in your genome. The average human has, I don't know, on the order of like 5 million polymorphisms. So these are variants in the genome. There's SNPs, structural variants, mostly SNPs, mostly single nucleotide polymorphisms, right? Which is what we're working with the sequence data. These are SDRs. They're a very specific type of they're tiny structural variants, right? Like they're insertions, whatnot, and so they're very, very variable in the genome. And so that's why in the 1990s, in particular, when our genomic resources were pretty limited, you were going to focus on STRs because they give you so much variation. Like I worked on STRs, in the early teens on an STR data set, and basically, you could get like many, many alleles, like many, many genetic variants at an STR because it's not like a single nucleotide polymorphism. Like you could get a lot of different variants through the different copy numbers and whatnot, right? So yeah, STRs are great. They pack a huge punch, but there's only 20 of them. And just like do the math, like there's limitations there.
Yeah. Exactly. So, I mean, you have two options. Well, anyways, you could look at, a few markers that vary quite a bit, and that's kind of a cost-effective way to go, particularly when technology doesn't support surveying genome-wide variation. Or you can look at a lot of variations, of which any one particular one doesn't vary too much, but in aggregate, if you look at lots and lots of variations, you can still develop the same kind of profile to distinguish one person from another.
Yeah, I mean, with the SNP array technology we're talking about right now, the arrays that are looking at specific polymorphisms that are known common in human populations, they go 500,000 to a million positions. And so, if you have so many genetic positions, so many markers, you can get really, really subtle inferences. So with the STRs, they're highly variable, but they kind of overwhelm you with variation, and you're not going to get that much granularity, just because the scale is a little different there. With SNPs, you can like identify, okay, these are first degree relatives, 50% related, identity by descent. Perhaps they're 25%. Okay, that's uncle niece, like, and this sort of thing. You could, and then like you go out to third cousins. You could even go out to third cousins. I mean, that's as far as I've seen, pretty robustly and pretty regularly with SNPs. You can't do that with STRs. And so with STRs, you can kind of, traditionally what they said in the 1990s, I believe, is, well, STRs can eliminate someone at the crime scene, but it's much harder to make a case for a positive match because the positive matches are true, but then there's the issue of false positives that are going to happen naturally. And so if you have enough cases, you're going to get a substantial number of false positives. And way our legal system in theory is working is that give people the benefit of the doubt, and you would much rather have a guilty person get off than an innocent person be prosecuted. And so it's just very, 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 very rare to have a false, like, basically very, very rare, where the rejection of someone at the scene with an STR is not correct. On the other hand, a match could be a problem, right, David?
Yeah, if we were to go super high level just for someone that doesn't dabble in markers and genetics, if you were to consider the case of you and me, if we were brothers, 20 STR markers, if we're brothers, we might share half of our DNA markers. And so that already cuts down the power of the STRs to 10 markers, right? And so the issue is that if you're my cousin, how do you detect that? Where's the sensitivity in detecting that with 20 markers? You might share a low few percent of markers with me, but you can't sensitively detect a few percent when you've only got 20 markers. So I think it just comes down to, you need a certain density of information, a certain amount of information to make fine grained assessments of relationships, particularly these longer distance relationships. And there's not a right or wrong way to do it. It's just a trade off. And so if you're looking to index somebody so you can track their serial crime spree that they go on, then STRs are a very fast and cost effective way to do that. And you brought up other good advantages as well. The challenge is that if you're not in the STR database, if you're not in the CODIS database, what do you do? So give you two examples. There are folks that go missing and end up unidentified every year, and this accumulation of folks that are never identified. The National Institute of Justice calls this a silent mass disaster. I never knew about any of this when I was training at Baylor. I was studying, you know, mutated DNA in cancer tumors. I never knew about this problem of unidentified folks, but there's tens of thousands of these folks that are unidentified. A lot of them are the victims of crimes, and how do you pursue justice for someone that's not identifiable? So some of them are not the consequence of a crime, but they're unidentified nonetheless, and they should be reunited to family. And CODIS identifies these folks less than 1% of the time. So you could run CODIS tests on 100 people that have died, um, you know, through some chance or another, and you may not even get one identified, and that's really just the nature of the composition of CODIS. It's not dominated by victims. It's dominated by perpetrators to crimes, and usually serial offenders, and or convicted in a court of law in
Yeah.
most states. And so, but the other thing is, like, look at the end the backlog movement, right? There's this initiative spearheaded by the DOJ. It's called SAKI. It's a sexual assault kit initiative, and the idea is that there's all these sex assault kits that have been collected as a result of a sex assault, and what they do is they want to run these kits. They've been sitting and they want to run them because running them may help identify the person responsible for the crime. It all makes sense, but even if you look at the national statistics for how often you can leverage CODIS to identify someone from a sex assault kit, it's like 15%, 1 5. So 15% of the time, 85% of the time, you don't know who the person is. So
Yeah.
CODIS is a powerful system, and it will remain so for a while, and it serves the purpose it's intended for, which is to track people that are convicted of crimes, and to observe if they are to commit future crimes and leave DNA at the scene. But it doesn't really solve the bigger issue of, like, how do you identify people from a crime scene? How do you identify victims and reconnect them to family? And how do you identify perpetrators that have gone undetected and for which there really hasn't been any other leads in any other aspect of the investigation? So for all of those reasons, and this is like the longest intro ever, I spent a decade doing, biomedical research and clinical diagnostics, and we got to this point where we felt there's a clinic probably a laboratory in every street corner in America somewhere, almost every street corner, where you can do a lab test to learn about a medical fact. But where do you go? Where do you go to process these growing backlog of sex assault kits that are tested but not solved, unidentified remains that just stay unidentified? And so we built a company. It's called Othram. Othram, and so we built Othram and it to this day remains the only in-house facility in the United States or Canada that performs this advanced kind of testing, and it allows us to enable human ID for investigators from crime scene evidence. And in contrast to the traditional methods of collecting 20 markers, we're leveraging that same Illumina sequencer that we talked about earlier to collect tens of thousands to hundreds of thousands of markers. So now all of a sudden we have sensitivity and we can detect very accurately relationships that are going to be more distant than just someone to themselves or their child or their parents. And we also have or their siblings. And we also have other information we can, we can gather by, biogeographical analysis made possible by tens of thousands of markers that help us learn something about a case. And these cases, when they go cold for a reason. They go cold generally because they've exhausted all other leads. There's not any more information that can move things forward. So,
Yeah.
anytime you can get more information, you should, because you don't really know up front what you'll need, but if you take the approach of gathering as much intel as you can from crime scene evidence, then some amount of that information could be valuable in producing a lead. And even the smallest lead, even the smallest clue, could move people in law enforcement in the right direction and help restore someone's identity or find out, who's responsible for their death.
Yeah, I mean, one thing that I think we need to emphasize here is going from 20 markers, and so you're going to whole genome sequencing, and there's issues with the quality of the DNA, how many markers you can get. But I mean, in theory, whole genome sequencing is the whole genome. That is just all of the information that you would need on someone. And so, this allows you to do a lot of different things. It's not a single purpose tool, it's a general purpose tool. So, you could do like the functional analysis where, okay, what does this person look like, right? So, you create like some sort of, you know, portrait based on their morphology and their pigmentation, or, figure out the biogeographical stuff like what's their ethnicity, what's their breakdown, this sort of stuff. But I think the biggest thing that has really come into the public eye, and why both of us kind of got interested in this topic recently, was the Golden State Killer event, or the apprehension of the Golden State Killer. Could you actually review that for the listener, people who might not be totally familiar with that?
Yeah, sure. And I think that I would point out that there's a lot of things you can do with DNA, but I like to gather information that I know is precise and can produce factual leads, and I get that a lot of folks have been exploring, facial morphology and such, but we tend to just focus on trying to establish clues to identity. From my perspective, it's like, who needs a face if you can get a name? So and that's just been kind of the more successful angle, and that's why we focus on that kind of information. But who knows what will be possible and available in the future. To review the case that you're asking about, there was this guy. He was nicknamed a lot of things, including the Golden State Killer, and he went on a rampage, sexually assaulting and murdering women for a few decades, and then he kind of vanished off the radar, and he just left a trail of unsolved cold cases, and it was later determined, I believe, that he was part of law enforcement, and so maybe he knew when to get out of the game. He kind of retired around the time the DNA testing became a thing, but he had remained unidentified nonetheless. He was never put into CODIS, and so he wasn't identified through CODIS. And there were some really smart investigators. By the way, this story predates the existence of my company. We weren't working on any of this yet. We were still in the formation phase, and so there was a joint effort by these smart agents at the FBI. One of them being Steve Kramer. He's since gone on to become a kind of the expert at the bureau for how all of this genealogical research and family tree research can be done. There was a local investigator at the law enforcement group. His name is Paul Holes, and he's since retired. But this was a case that he really wanted to crack, and was fortunate enough to crack before he retired. And then a very, very, very skilled genealogist. Her name is Barbara Ray Venter, and so the three of them, and lots of other people involved too, but the three of them kind of set on to see
But
if there's a way to get.
that's an interesting last name, Barbara Ray Venter.
Yes, ex-wife of Craig Venter. So there's a little bit of a tie-in. I think it's incidental, but yeah. So there was an effort to basically take some of the remaining evidence from the sex assault and to determine if there's anything that can be gleaned from this DNA. And the idea was that, look, Barbara, for example, she's a very skilled genealogist. She's working these cases for folks that are trying to reconnect to relatives, or sometimes people are doing genetic genealogy to find their biological parents that might be adoptees. And so the idea is like, what if the Golden State Killer was the adoptee? How do we find his biological parents? And so the first question is like, how do you build a profile? And so we were fortunate that there was a lot of DNA in this case. There was a lot of cases, and they built a profile. And once they built the profile, they then uploaded this profile to a public database called GEDmatch. And for those of you guys that are not, which I imagine is most of your listeners are not kind of pro genealogists, when you test with one of these companies like 23andMe or Ancestry or Family Tree DNA, your data gets deposited into a database, and you can use that database to essentially identify possible relatives. Well, these companies don't intercommunicate together. At any rate, 23andMe and Ancestry don't. And so you have two options. You can test at 23andMe and Ancestry, or if you want to bridge the divide, suppose you, Razib, have tested at 23andMe and I tested at Ancestry, but we want to know if we're related. Then what we would do is we'd both upload our data. We'd download our data from our respective companies, upload it to a public database, in this case, GEDmatch, and then we can do direct comparisons to see if we are in fact long lost brothers. And so what they did is they built a profile for the Golden State Killer based on this crime scene DNA, and they uploaded it to GEDmatch. And did some other work. I'm oversimplifying here, but they uploaded to genealogy databases. They identify some relationships working back from, I believe, second and third cousins, and it takes more than one match. It takes a number of matches to kind of figure out who someone is. They're able to work back and eventually identify this guy, and narrow down the pool to where they eventually identify this guy as a candidate. And then what the cool thing is that after they developed this hypothesis that he was the person responsible, they used the conventional STR testing, which I told you is excellent at doing the comparison of you against yourself. They used conventional STR testing to confirm that in fact his STRs matched. His STRs matched the STRs at the crime scene. So this is a fascinating thing because, as I told you, STRs are not good at finding people, but they're really good at confirming identity. So the way the model works is you use the STRs to confirm the results of what you do with these advanced DNA testing that uses the hundreds of thousands of markers. And in using the two systems together, you kind of get a double validation. Um, you know, two different methods with two different labs uh, coming to the same answer. And the STR testing, at the end of the day, is kind of what is the established and accredited and court approved and recognized method. So you use the work that Othram does to generate leads, but then you confirm those using the same standard forensic framework so that you know, in fact, that you've identified the person that you think you've identified. It's really cool. And so the Golden State Killer was one of many initial cases that demonstrated that the idea is possible. Like theoretically, it is possible to identify folks in this manner. And then there was kind of a rush of people that jumped in to go do genealogy to help work all sorts of crimes, which I think is just a wonderful thing because genealogy is cool, but here's a new application of genealogy that can do tremendous public good. And so it's very fascinating to watch. And what we do at Othram is we basically focus, on trying to make sure that we can build in a very scalable and robust way the best representations of these profiles. Because if your profiles are noisy, if they've got mistakes and errors and just kind of artifacts from what will be inevitably the result of not optimal DNA. You have to remember, like forensic DNA is not like consumer DNA that you swab out of your mouth or,
Yeah.
or pull from your bloodstream. This is DNA that's got all sorts of problems with it. And any of that noise or artifacts makes it into the profile, then you'll end up with a substantial you know false negative problem. Like you you just won't see things. I mean, if the whole model of relationship testing, right, is that you and I are more related if we share more markers. If the markers are wrong between us, then we'll just end up looking more distant. And in the worst case, we may not look related at all. So our
Yeah.
focus at Optum is to basically build the most faithful representation of markers, to do the best job we can to aid in the investigation of someone from a crime scene.
Yeah, so I'm curious about this aspect. You're saying that the DNA obviously is not high quality, and some of this stuff dates back 20 or 30 years. But one thing that I'm wondering about is ancient DNA has changed a lot of things in terms of what people think that they can do, and obviously you're not getting hyoid bones or whatever. Like some of these are rape kits and whatnot. But I mean, what have you learned about trying to get information out of these old samples? Are they being preserved well, or are they not? Is there a lot there that's being left on the table?
It's a mixed bag, but what I'll tell you is that, if you look, if you think about forensic DNA evidence is like an iceberg, and there's going to be some stuff at the very tip of the iceberg that's above the water, and that's going to be like, someone's a homicide victim, their entire body's on the ground, they were found just recently, and there's like, buckets of blood, and so there's reasonably decent DNA, single source, you can grab that, and there's probably a lot of ways to test that and get good results. Then underneath the water is really the bulk of the casework, which I guess doesn't make it to the news, but it's a really tricky stuff. Sex assault kits, as you mentioned, sometimes fall into that category. A lot of older unidentified persons, just evidence that's imperfect. And so there's a couple of things that we found. A lot of the time, the quantity of DNA is limiting, so there could be very little DNA. When you do a 23andMe or ancestry test, you're collecting with the swabs 750 to 1,000 nanograms of DNA. So just in contrast, like we generally work on a sub nanogram level. I believe we've identified someone from the least amount of DNA. I think publicly reported. I think we have the record for like lowest amount of DNA used in a published law enforcement case, and it was 180 picograms. It's like 20 cells. So you're contrasting like a fifth of a nanogram with 750 to 1,000 nanograms. So the very first thing is that when you work in forensics, you have to be accustomed generally to sub nanogram quantities, and sometimes to like just a small hundreds of picograms, and that's an adjustment in technology and in method. The next thing is that the DNA is often degraded, so DNA generally exists in long contiguous chunks of DNA, and as it degrades, it breaks into pieces. There's all these double strand breaks that accumulate, and if the DNA degrades, which it does over time or in response to heat or chemical insult, if it degrades too much, it can get into such tiny little pieces that it's really hard to read with a lot of modern DNA testing methods. So that's the other problem, is that you have not just low quantity DNA, but the DNA is really degraded. And so not all that DNA is usable because some of it's degraded to tiny little pieces, some of it's okay, some's on the border. So again, a kind of a different approach and a different methodology to ensure you can still capture information from these smaller degraded fragments. The third thing that I want to mention is that a lot of these remains, and even sex assault kits, they have other kinds of DNA on there. They have non-human DNA. You know, people find bones in the woods, and they've got bacteria, they've got other stuff growing on it, and DNA sequencers are unbiased. If it has DNA, they'll read it, and so you could very we've had cases where we've performed the DNA extraction from skeletal remains, but maybe less than 5% of the DNA is even human. Most of it's just bacteria and other stuff. And so how do you deal with a scenario in which there's a high non-human DNA load? And the last thing is DNA mixtures. So again, like in a consumer company, you're swabbing your mouth, you're getting high quality, high quantity DNA, and it's fresh and it's single source. You'd hope it's only one kind of DNA in your mouth. And when you look at some of these crime scenes, there could be mixtures of DNA. Maybe they lifted DNA from an object that more than one person's touched. Maybe it's a sex assault kit and there's DNA from the victim and from the person that assaulted them. Maybe it's a piece of clothing and there's DNA from the person wearing it as well as the person that attacked that person who was wearing it. So being able to deconvolute mixtures of multiple human beings in a DNA extract, that takes some work, and some of this is laboratory work, some is computational effort, and some is both. So, just to say that there are of course going to be low hanging fruit cases that can be approached using a variety of methods. And I think the Golden State Killer case fell into that category. And it's fortunate that it did because it was a really, really powerful illustration of what's possible. And I think it really ignited the interest in the space. But also to say that the bulk of casework is going to be problematic in some way or another. Usually one of those four things that I mentioned.
Okay, so I mean, we've been talking about the methods of the science and all of this stuff, the history of forensics. What's the most interesting case that you have been involved in? And I know we're friends, so you send me these cases and stuff like that. You're starting to get them fast and furious now, so I think you got some a
We,
selection
we have a
to make.
fire hose of cases. I don't know if there's like one case that's the most interesting. Um, there are some interesting things we've learned along the way. I've always wondered like why are people unidentified, and I can tell you like, for example, for unidentified persons, it's interesting because a lot of the times the the record of the person missing and then the discovery of a body, they're either separated by time, so maybe the person is reported missing on 1 year, but years later the body's found, or they're separated by distance. So we helped identify a girl. She had gone missing in 1966 in Kansas City, and then she ends up in Pecos, Texas, at the bottom of a swimming pool. And so, how would you connect those events? I mean, there's just I mean, the family was looking for her immediately, but they were states away, and they had no reasonable assumption to make that she had been in Pecos, Texas, and so geography can sometimes separate. We had a guy we identified, helped identify, that was a homicide victim, and he was reported missing at one point. He was last seen at another point, and his body was found at a third point. And it turns out part of the story is that he had been murdered and then weighed down in the lake, and his body had surfaced years later. So again, like the timing's all off. So you wouldn't necessarily put the records of the missing person and the discovery of the unidentified remains together. So you have these scenarios where you have really good investigations, kind of stubs of two investigations, one into a missing person and one into an unidentified remain. And these investigations have been done very well. The law enforcement did their job, everything's good, but they don't connect because of this separation of geography or time. And DNA testing is that magical force that can essentially connect those two things together. And once you connect the two lines of investigation together, it's amazing. All of a sudden, it all makes sense. You piece together the story, and very often you figure out what happened. If they're a homicide victim, you might figure out why and who is responsible. So that's one kind of interesting thing. Another interesting thing is, a lot of the cases, there's a government database called NAMUS, NAMUS.gov, and they catalog a lot of the missing and unidentified. And when they find skeletal remains, generally they find these people, like, quite some time after they've died. So it's hard to really figure out who they might be. They use forensic facial reconstruction and anthropological tools to try to guess at ancestry or some kind of ethnic origins, just so they can describe the person minimally to maybe produce a lead. And what we've discovered is that it's not uncommon for the anthropological assessment to just be completely wrong. So we have a case that we literally just announced, I think, just days ago or maybe a week ago, and it was a woman that, based on dental records and the kind of dental work they had, dental work they thought had only been performed in Asia, and this was in the early '80s that she had vanished. And um, this body's found in the woods, and it's in Montana, but they designated her as Asian, and it was odd because it was almost, they also said specifically Japanese. And so that's another
Okay.
issue, is like when you make a determination about something, the more specific you are, the more certain it sounds. It sounds certain if you say someone's Japanese. Might sound more vague if you just say I think they're Asian. Other anthropologists had pegged her as perhaps of African ancestry, and when we took on the case, we did the DNA testing and found that she was in fact a multi generational white person from Washington State. And so there's this idea that there's it's not uncommon for us to see conflicts in assessment from the anthropology data and from the genetics data. And obviously the data we're collecting from genetics is more dense, it's more rich, there's more information, so you are going to have more precision when you use DNA testing. So that's another really interesting finding. And I have to say, in this case of this woman that was unidentified, but described as Asian and Japanese, it's unfortunate because her son had been looking for her, and my understanding is that he had stumbled upon this case and kind of discounted the possibility on the basis that she was listed as Asian. Of course, he's not Asian, so not able to do that. Um, and so these are the kind of interesting things that we find. The
Yeah.
last thing I'll tell you is we work crimes. We helped identify murderers and rapists that had committed these sex assault homicides in a number of cases that have been announced. And in every case, they weren't in CODIS. So the law enforcement always checks CODIS before coming to us. So here are people where there is evidence of a sex assault. There's DNA evidence left, but they can't identify the person. And it's remarkable. A lot of these folks that end up being identified as responsible, they're not the kind of like movie villain that you would expect. Some of them aren't even necessarily mass perpetrators of the crime. They're ordinary people that have done terrible things and are just hiding in plain sight. And again, there's just no lines of evidence. It could be a random encounter. There's no reasonable way to expect, much like with the unidentified folks that are separated by time and geography. There's no reasonable way to connect these people back to the victim. But DNA testing can do that. DNA testing identifies who is at the crime scene, and then in conjunction with other evidence can help figure out who is responsible. So I would say those are three really interesting things that have emerged. The last thing, if you want to have a bonus number four, is that we've had cases where the person that was missing was adopted or lost touch with family. So those are other reasons. I mean, you have to imagine, like, when a case like this goes cold, and especially for unidentified, when they're not identified by anyone, there's usually a reason. There's something's happened. They've disconnected, they haven't been in touch, they were adopted. Any one of those things. Maybe their close family members have since passed on, and there's just no one left that knows. But there's always an explanation, and DNA is that connector that can connect these seemingly unrelated or disconnected lines of investigation into a coherent explanation of what happened.
Yeah, yeah. I mean, it's fascinating to me that there's all this stuff that people thought they knew, and then you go back and you check it, and they had it wrong in the first place, and that's why it was never actually closed. So it looks like there's going to be a lot of cases where people are going to review the old forensics. And for listeners, I mean, I'm sure they know the many scandals that have plagued forensics. FBI forensics labs recently, with their various methods like bite marks or hair analysis. I mean, they're not really scientifically sound. And so, one of the things that forensic DNA is doing is bringing a legit science into the field, and that's going to cause some issues. I guess I want to close out with not necessarily a negative note, but I think some people are going to worry. Okay, so you're a forensics company and you're doing all this stuff and you're cooperating with the government. Where are we going here with privacy and various concerns about, just ethics and forensics? Like, I mean, what does that mean to you? I mean, are you worried? Like, what are people saying?
Well, I can talk all day long to you about genetics and DNA testing. I'm not an expert in all these other issues, but I'll share some observations. So number one, like, there's you can start with, like, is there really a point to even pursue this technology, right? Like, why take the risk? Why get involved at all? And I think what's come out of the discussion that we've had today is that there's tremendous humanitarian value to reconnecting people back to their family. These are people that are unidentified, usually the victims of crimes, and they just would never get reconnected back to family without such a technology. These techniques are applied in cases where they've tried everything else. They've tried to draw the face, do the facial reconstruction, anthropological analysis, CODIS testing. If there's fingerprints, they do that. They check dental records. There's nothing that connects these people back to an identity. So there's a huge humanitarian value, and everyone deserves a name, and everyone deserves to be reconnected to family. And reconnecting them to family allows the surviving family members to kind of get closure, get a sense of peace, and move on. Um, in a lot of these cases, the world continues, right? Like this case of the girl that died in the pool in 1966. It's been decades. Most of the world has moved on, but it's just her family had not. Her siblings are in their 70s and 80s now, and they had not moved on. And it meant a lot to them. It was really important to them to know what had happened to their sister. It's very important. And so that's one
Yeah.
thing. Likewise, in a crime, same situation. You have scenarios in which these families cannot move forward, and they're unable to they're unable to get peace or closure. They don't understand what happened. These people that I told you about that were assaulted and murdered, and the killers never identified. And there's one such case that we worked in Texas. It was the sexual assault and murder of Carla Walker, and her family was really appreciative. Her brother has dedicated the last 45 years of his life. He joined law enforcement. I mean, he dedicated his life to trying to find out what happened and to bring the person responsible to justice. So just can't stress what the humanitarian value is of allowing at least the people around that victim, the friends, the family, to get a sense of closure and move on, and begin the healing process when something like that happens. So that's one really big important thing. Um, but the other thing is that we trade, and as a society, I think we trade some aspects of privacy sometimes, when there's a value to be had. I mean, your cell phone has lots of wonderful things that it does to enrich your life, but your cell phone also, to extent, can compromise some aspects of privacy, and so you just make that trade off. And I think there's a trade off here. I think that you can do a lot to mitigate privacy concerns. For example, at Othram, all we do is human ID. We don't do medical research. We don't do other things. Um, when law enforcement searches these databases, they're only searching people that have consented to have their data searched. If they've not consented, those profiles are not searched. And so there are things you can do to kind of limit the scope to people that have consented, limit the use of how you're going to use that data. But ultimately, you're pursuing, I think, what's a really important cause. There's really no other way to solve these cases, and even at the search level, you're not even really trading in people's genetic information. When you do a genealogical search, you're actually using the data to actually infer relationship distance, right? Am I a first cousin, a second cousin? So if you can minimize the information that is shared, restrict it to those that have opted in, and then really focus the discussion around human ID, which is what I think should be done, then I think you have the beginnings of a framework that can make people comfortable. And at the end of the day, some people won't be comfortable and they shouldn't be compelled to participate. But for those that do feel comfortable and want to help, this is a way to really bring a lot of value to society. And so I think it's a good thing. And I think, like all good things, it needs to be leveraged in a way that is consistent with rules, laws, regulations, and certainly there's a lot of room for discussion about how to do it in the best possible way. But I think this is the future. I actually think it's the present. The future is going to be deploying these techniques to every case and not just a few that you see in the news. I think we're
Yeah.
going to transition from exceptional events to what will become just expected ordinary events. And so I think it's time to have that discussion. But I think the technology's here, and I think it's going to do a lot of good for the world, and I think it's going to
Yeah.
close out a lot of backlogs.
Yeah. I mean, I think the way I would close out here is like, in this discussion on science, policy, crime. The ultimate thing is we have the technology, and whether we use it or not, it's up to us. I think you've made a proactive case. I mean, you don't have to sell me on it. Maybe some people out there, but I think that the proof is in the pudding here. If you solve crimes and if you identify missing people, I think people are going to want to do this.
I think so. And I think, look, you have to share. We have a website that I encourage everyone to check out. It's called dnasolves.com, dnasolves.com. And we chronicle cases that we have either solved with law enforcement. Law enforcement's announced them and they've leveraged our technology that we're trying to work on, and we might need help from the public, or even cases that we're trying to fund because not all agencies have funding yet for these technologies. And so there are some cases we actually just crowdfund on DNA Solves. And I like telling the stories. I like having these discussions with you and others because every time people see the positive outcomes that are possible with the technology, it helps kind of drive the adoption of the technology. People hear about a story and they think to themselves, I have a case just like this I could benefit. And so I think it's important. I think it's important just to celebrate the successes, discuss the concerns, do all this openly, because as people become comfortable and chart a path for how to use technology, like I said, I think it's going to do wonderful things. And I expect it to be one of many tools in the toolkit. I mean, law enforcement have a lot of tools available to them. They have the STR CODIS system. They've got fingerprints, dental records. Now they've got the kind of technology that we're building at Othram, and we fully hope to then deploy that to all agencies. Because that's justice, right? When you can democratize the use of these techniques for all investigations and not just the most important, and I say that in quotes,
Yeah,
the
yeah.
important ones.
For sure. Well, it was great talking to you, David. Maybe we'll have you on some other time, and let's keep in touch. Everybody out there, just Google Othram, DNA Solves. There's a lot of stuff out there. It's super interesting. If you're interested in, DNA science plus, true crime is a whole field into itself. There's a lot of people who are kind of mixing it all together. We live in the age of cultural mashup, and it's great that David is in the middle of that.
Well, I appreciate you having me.
This podcast for kids.